Hello, my name is Tom Benke, Senior Application Engineer with Simtech Automation. And in this short video, I'm going to show you how to connect a Festo 12-bit analog device to an Emerson RX3i controller. For the physical setup, I'll be using a small air cylinder from Festo. You can see the part number there. To that, I'll have it connected to a position transmitter that's communicating via I/O link into a 4-channel I/O link master device. The I/O link master will be communicating into a Festo PROFINET master device. And with that, I would normally connect the PROFINET directly into LAN 2 of the Emerson RX3i controller that I'm using. However, in this case, I'm gonna, just to make things a little easier for setup and to show what's going on, I'm gonna have the PROFINET master connected into a switch, which will also be connected to the PROFINET port on the Emerson CPL410, along with the programming port for that PLC as well. While I am doing this with a CPL410, the same basic idea will work with any RX3i PROFINET-based processor, whether that is a rack-based solution with a PROFINET controller from Emerson, or any of the other standalone CPUs that offer a PROFINET port. And of course, into that switch, I'll have my laptop connected so that we can visualize and see what's going on. Before we get moving into programming on the PLC, I wanted to get into Festo's automation suite and show the hardware I'll be using. This is basically the same thing we saw on the previous slide. However, in this case, I'm looking at just the Festo components via a PROFINET connection. Kind of before I show what we're wanting to see, very quickly I want to show that from within Automation Suite, I can look at the support files for the PROFINET master device, and I can look and get my device description files, my GSDML files. This file is needed to load into the Emerson controller so that it knows how to talk to this PROFINET device. So from within the software, just very easy to go grab the GSDML file and have that on your local PC. So once you have that file, that GSDML downloaded, showing you real quick here, this is live data coming off of the cylinder through the position transmitter. And as I move the air cylinder in and out, you'll see the value of what the position transmitter reads is changing. So that's all the way extended. Read that number as 50 millimeters, so kind of divide what you see there by 100. And I'll go ahead and push it back in, and we'll see it go back down to 0. So basically what I want to do is be able to see those exact values as what the RX3i controller would see through that port. So from here, we'll move on to moving into Machine Edition from Emerson.
Okay, so now we're in Emerson's PAC Machine Edition software, and I've created a new project targeting the CPL410 processor. I've gone ahead and dropped down the CPL410 hardware system, and we'll add a PROFINET I/O device. This is where we saved a GSDML file from Festo's Automation Studio, and as you can see here in the PROFINET device catalog, I have already said I have this file, and it will go ahead and populate this tree with this device. So I'll go ahead and add that in. So now we have the Festo PROFINET device sitting in my PROFINET tree. A couple of key points. First of all, the device name came up as default as a CPX-AP-I-PN. And if I flip back over to Festo's Automation Suite, I can see that that matches the name of the station. If you're not familiar with PROFINET, PROFINET is a name-based system, so having these two match is important. Other thing to note here is the IP address of that PROFINET device is 192.168.1.2, and I need to make sure that matches in PAC Machine Edition, which it does. So we're good there. My next step is going to be to add the IO-Link master module. This is the second device, and this is what communicates with our analog device. So I'll go ahead and get this added in. And we can see that's now populated in the tree. And the last thing I'm going to need to do is add the analog, the positioning device. So I'm going to change my submodule list, and I'm going to go and show here in Festo's Automation Studio. We'll look at that device, which is here, and we can see that this option right here, this variant 4, means that it is a 4-byte device. So I need to make sure that I pick that option. It's 4 in, 0 out. And for good practice, I'm going to go ahead and deactivate all the other ports. Okay, so we are now set up from a hardware standpoint with all of what we need to start looking at the data from the analog device. So the next thing I'm going to do is go ahead and open that, and I can see that the input data is going to be mapped to AI1. So what I will do to make things a little easier is I'll create a variable, and this will be a word variable. I'll call it SDAT just because that's the part number of the positioning device that we're using. And for its reference address, I need to put in the %AI1. So all of that now is set up. I guess one additional thing we can go ahead and do is set a watch on that variable so that we can look and see its value. So now what I'll do is go ahead and connect to the CPL410. And I'm going to go ahead and get into programmer mode. I'm going to stop the processor that's running. And the next step will be to download and start. So I'll pause the video before I do the download. And after the download completes, I'll pick back up. Okay, so we have now downloaded the project to the CPL410, and we are online with the processor. And as you can see here in the data watch area, the variable that we created, SDAT, is showing a value, but get back here into Automation Suite, and let's look at the process data from there. For where the position sensor is set right now, we would expect an output of 10, and what we're seeing is obviously not 10. So I'm going to slowly move this position, or the cylinder rather, out, and you can see the value in Automation Suite kind of grow as we expect, slowly. And that SDAT variable is just jumping all over the place. So that's obviously not what we want. Now, the reason this is happening is that the bit order of data coming over is not in the format that the Emerson hardware is expecting. So we have to do a little bit of manipulation with that bit data. So in order to handle that, we've created a user-defined function block from within Machine Edition. So let me get here and let's look at the main program. And under UDFB, I've got a 12-bit Festo user-defined function block. So I'll go ahead and add this into my project, and I'll go ahead and wire it up. The way a user-defined function block works is basically you have a template that you drop into a project, and then you need to create an instance of this. So at this point, it's waiting on me to name this particular instance of this user-defined function block. So I will go ahead and give it a name. I'll just call it test. And we want to need to add an input. So I want to go ahead and put SDAT as my input into this. And we'll also create an output variable that will be the fixed and hopefully aligned variable. So let's go here into variables. You can see that the output's been added. And let's just, we're going to need to change the data type of it from an integer to a word. Okay. And at this point, we're now set up to use this user-defined function block. This user-defined function block is available from Simtech. We'll also include a link so that you can download this as well. And so our next step will be to go and download again to the processor with our updated logic here that will hopefully fix this input from the Festo position sensor. So I'll go ahead and pause the video again while I download the new project. So we've downloaded the application to the CPL410, and I'm going to go ahead and set up a watch for the output variable, just so both values are sitting here together in the data watch area. And these two should now be tracking really closely. So this value again would be divided by 100 to get the millimeter measurement. So seeing just a little bit of difference between the two, but for the most part they're tracking together. I'll go ahead and start moving the cylinder in and out, and you can see that the current value and the output value do track much more closely together. Again, just a small, looks like a small amount of error there, but it's probably within the tolerance of the allowable error for this system. So at this point, we now have a working output value, and we're getting values we expect. But if there's a case where we weren't, I want to go ahead and show you how to fix that, and that's where this scaling factor comes in. So the way that I would address this is go ahead and put a constant of 1 in at the scaling factor. I'll apply a word-for-word change here in the Emerson system, and you can see that the output is now giving a unscaled value, so it's 191, whereas in the Festo Automation Suite we're seeing 933. So probably what I'll do is I'm going to move the cylinder kind of to a midway point. Probably there is good. The output's now showing a value of 591, whereas we're expecting 2886. So to fix the scaling factor, I'm just going to put in the 2886 value. I'm going to divide that by 591, and I get a scaling number that kind of looks very similar to the number that I had previously. Go ahead and copy that, and then I'm going to begin an edit here, and we're going to make that the 4.88 value, and we'll go ahead and accept that edit. So now we're getting an output of 2886, and that matches what we see here in the Festo Automation Suite. Go ahead and start moving that cylinder around again. We can see that the two numbers now still track very, very closely with one another. So that's how you would address a scaling issue if that was to occur. So hope this video was useful for you. Again, the contents of this user-defined function block are relatively easy to put together. Just takes a little bit of looking at what the data bits are doing and creating a way of handling it. Again, that user-defined function block is available for download, and if you have any further questions, feel free to reach out to Simtech Automation. Thanks.